So as mentioned, forecaster, I've been there for 9 years now, and I recently got hired from the regular forecaster to the service coordinator part, which part of that job is education outreach. I interface with our customers, and you're going to hear a lot about customers because the thing I want you to come away with today is not only all the interesting things that the sun is doing, of course everybody wants to know about the aurora, but all the things that are actually going on that you've probably never realized when it comes to significant space weather. The notifications we're making, how important that can become, who we're talking to, which gets to the very top, as you're going to find out, and then what's going to happen if we have a big catastrophic type space weather event that affects our technology and our infrastructure. Because it's coming. It's still yet to happen. The last time it happened, you're going to find out, is probably 1859, before we had all the wonderful technology that we have now, but we're overdue. So it's just a matter of time. So fortunately, as you find out, our government really does a lot to make this better, space weather forecasting, and plan for a major catastrophic event. So, all right, so you can't see here, but because we know astronomy is so deep, but this is not what space weather is. If you could see it, I got a pretty nice picture of the North American Nebula over here. The Pleiades, for those who know the horse head up there. This is all just from my own backyard up in Berthoud. Thanks, there you go. So, yeah, but that's not what space weather is. It's also not this. It's not the galaxies out there. Those that don't know, we're looking at two types of galaxies here. We do get radiation from these galaxies, those in the form of gamma rays, they're called. They make a long distance journey, and believe it or not, astronauts are actually more exposed to this than the harmful particles that come from the sun. This here is the Helix Nebula. This is not space weather either, but those of you who know a little bit about astronomy, supernovas can bring in cosmic rays and energetic particles themselves, like our sun can produce energetic particles, as you're going to find out. Nova's not so much, like this beautiful Helix Nebula here. And finally, it's not Jupiter either, but the aurora has been seen over Jupiter. So space weather does impact other planets. We're responsible at SWPC for the Earth realm, and near Earth, NASA is responsible for elsewhere in the solar system. There you go, you can flick them back off them. So if you could join us in person at Boulder where I work, this here is the main area where you look in two giant windows into our forecast office, and that's the heart of it right there. 24 hours, 7 days a week, somebody's always staffed in there. I had to do an emergency fill-in on Tuesday night, I think it was, and worked from 8:30 at night to 6:30 in the morning. And forecasters are there right now doing their job, paying attention to what's going on. We do fall under the National Oceanic and Atmospheric Administration, NOAA for short, which is where the National Weather Service falls under, and we are part of the National Weather Service. The National Weather Service role is the protection of lives and property. You all know this. Tornado warnings, we know what to do, right? The Weather Service has done a great job educating and warning us about it. But space weather, yes, it can impact our way of life, in some cases human health, but the thing we're really worried about is our technology and our society. So we are safeguarding society with actionable space weather information. So what exactly is space weather? Well, it's what's taking place on that giant ball of burning gas 93 million miles away, in that huge vacuum of space between the sun and the earth, and ultimately at, here, and around our planet. The government, highly interested in space weather now because there's historical evidence, historical events, even in our technology age, that we know space weather is going to impact things, and we rely so much now on everything, right? Siri, whatever. Want to turn on our lights, and the lights go on and off like he's doing over here right now for me. That instant, right? Turn on the water, it comes on. Well, we know that we could have a catastrophic collapse of our technologies here, which we refer to as infrastructure, even when it comes to space weather, whether it's satellites in space, the electric power grid, communications, whatever. It does impact these things. And the government has started putting out not only executive orders, but legislation, bills. There's working groups like this thing called the SWAG, the Space Weather Advisory Group. That's our Deputy Secretary of Commerce sitting up here at the White House. One of our folks just briefed the Vice President about space weather. It's a concern. And fortunately, it doesn't matter who's in charge, who the big boss is in the presidency. This seems to cross political realms. So even the Trump administration was digging into space weather. The Biden administration continues into it. So that's the good news, because we need to plan and be ready for this type of activity in its worst case scenario. And this is a kind of worst case type scenarios. This is what space weather could impact. And what do we keep developing? New things to tinker with in technology. We've got drones. Now we have to understand what can happen if there's a drone out there and it suddenly can't have the communication. What's going to happen to it? Does it affect people's lives? Could it cause a crash? Could it cause an incident? Railroad. Even fortunately in this country, space weather doesn't impact the railroad, but think about it. As you're going to find out, red lights can go to green lights, and green lights can go to red lights because of the way railroads operate. We don't operate that way in this country, but in Europe, they do. They don't want to have a train moving along and have a red light turn green. That'd be really bad, right? It could cause a catastrophic crash. So they're concerned about space weather, among many things, but that's just another one. So we may have certain concerns, other countries may have others, and together we all are working together when it comes to space weather. Even, what's the dog's name? Harley. Even Harley's interested. Look at that. So billions of dollars of loss can happen here. And the worst case scenario we're talking about is the loss of power. And it wouldn't be just for our country. As you're going to find out, other countries have suffered power grid collapses because of space weather events. All right, our forecast operations office. So now you're kind of going behind the windows into the forecast office where we all do our job in there. 24 hours, 7 days a week, as I mentioned, we're sending out watches, warnings, and alerts. So who's all familiar with a regular weather watch? Hopefully everybody. What about a warning? Does everybody know what a warning is and what to do? A tornado warning comes. Okay, we do the same thing. We put out watches, but it's really only for one type of activity. We put out warnings for a few types of activity, and then we do something called alerts. An alert is when it's actually happening. So the watch means it's the conditions are ripe for it. We do this out 1 to 3 days. Warnings means that it's imminent. We are now expecting it. The alert is when it's going on. And the reason we do alerts is because the technology operators and controllers need to know when it's actually happening. Not just that it's about to happen, but when it actually is. You can see some of our core partnerships listed here. We have more, and they're growing. The USAF is my old profession of 22 years, the United States Air Force. Huge partner. We couldn't do this job without their help right now. And as you're going to find out, the Air Force, yes, praise them to be, were really helpful in an event that happened that you probably are first time going to hear about it on December 14th. Aviation was at risk around the entire country because of a space weather event. NASA, we talk to the Air Force every day, several times, regardless of what's going on. NASA, for the benefit of the astronauts on the space station, we talk to at least once a day. When activity picks up, we call them more, and now they have to bring somebody in and sit counsel and mission control. FEMA, our emergency response branch of the government. You're going to find out what takes place at the highest levels of activity, how involved FEMA now becomes. So one of my jobs is to start training FEMA. I was just talking to region. There's different regions across the U.S. I was just talking to Region 2. That's out in the upper Northeast, New York, all the big northeast parts of the country, states, about space weather. And this is going to happen all around because they all need to be space weather ready when it comes to what this can do and be prepared for any catastrophic incident when it comes to it. The NERC, I'll get into that later. So the solar cycle. If you didn't know, the sun operates on a cycle. It's an 11-year average. It's not firm. It could be 9. It could be 13. And what that cycle is basically go from very little solar activity to peaks of solar activity. So the plot on the bottom left over, or bottom right over here, you can see these ups and downs throughout the years. That's what they are. The reason that happens is the sun is rotating as well. Okay, we all know Earth rotates every 24 hours. The sun is rotating as well. On average, it's 27 days. The important thing about it, and this is the driver behind space weather, is the equator of the sun, that middle of the sun, is rotating much faster than the poles of the sun. 10 days faster. Now, since it's plasma, and it can take it, it's not a solid rock like Earth, it can handle that. It doesn't break apart. But what it does mess with is its magnetic field. So imagine a nice bar magnet, and you're holding on to it, okay? And it's just a straight north-south. Now, the sun never looks like that. Its magnetic field is never perfect like that, but let's pretend that it is. Just straight north-south. I told you the center is rotating faster. So a couple of months later, it stretches it. A few months more, it stretches it further. Pretty soon, it starts to lap itself, and then it becomes this twisted up mess of magnetic field lines. So you no longer have this nice line. It's just this twisted up mess like a cat got out a ball of yarn and you're trying to put it back together again. That's what happens. That's when we get to solar max. That's when we start to have sunspots littering across the sun like right now. If you went and looked at the sun, just covered with sunspots I was in there working the other day, and there was 14 sunspot groups on the sun. Not just numbers, but groups. The sunspot number for that day ended up being like 200 something. I think it's the highest we've had this solar cycle so far. So things continue to pick up. We are in solar cycle number 25. The newest adjusted peak of activity for this is expected to be either this year or early next year. Doesn't mean it just shuts off and goes back to normal. It takes time. So it'll slowly come down. So this year, 2025, and even in 2026, we're going to be at the most risk, even though it's still very unlikely, but at the highest risk chance for one of these severe to extreme level storms that could potentially impact our technology and way of life. Notice sunspots can be quite large. You can't quite make it out here, but this here is planet Earth. This is the size of a sunspot group right there. 109 planet Earths can fit across the center of the sun. So these things become massive. But the thing we're looking for as forecasters here is not the cool sunspot like you might all want to observe with a telescope, safely with a filter, magnetic fields. I told you the sun becomes twisted up. Well, those magnetic fields pop through the surface of the sun. That surface is where light escapes that we're looking at here, the photosphere of the sun. And if it's strong enough, a sunspot forms up. So sunspots are actually they're dark because they're cooler. A couple of thousand degrees cooler than the surrounding surface of the sun. But for us forecasters, we're looking and focused on its strong magnetic field because that tells us a lot about whether or not these sunspot regions are going to produce or be the source of a solar flare. What's a solar flare? You'll have to wait for that, but the solar storms. So the sun rotates, I told you. Here you can clearly see that. This is about a week and a half, something worth of imagery. You can see a huge sunspot complex up on the top, the north part of the sun, rotating along. You can see some sunspots rotating to view, some emerging right in front of your eyes up there to the north as well. All these magnetic fields popping through the sun. Right now, as I told you, if you looked at it, it's just covered in sunspots. A huge group is about to rotate off. And because I love confusing people, I mean, that's what we do in science, right? You think of a map, right? So when I start using directions, try to keep this in mind if you can. I'm going to try to avoid it for you, but keep in mind. North is north, south is south. This side over here, that's east. This is west. Okay, not what we're used to looking at, right? Just maybe think of it like this. The sun rises in the east, it sets in the west. Things are rotating into view from the east, rotating out of view to the west. That's my only theory for how the naming of the coordinate system came up for the sun there. But yeah, that's a sunspot group. To us, a huge, giant magnetic cluster that we need to analyze very closely. What are we concerned about when it comes to space weather? Well, a lot of different things that we're focused on in forecasting, but these are the big three that I would like everybody here to be familiar with. And these are what drive what's called our NOAA Space Weather Scale. It's a 1 through 5 scale, kind of like the hurricane scale. And it's for 3 main categories. Those main categories are impact-based. The impact is solar radiation storms. Well, that sounds kind of frightening, right? What would you all do in here if your favorite Denver weathercaster came on TV and said, oh yeah, this rain's going to end, it's going to be a wonderful weekend coming up, blah, blah, blah. Well, hold on. I've just been handed a bulletin from the National Weather Service. A solar radiation storm has been issued for the entire planet. What do I do? What does that mean? Oh no, right? Well, you're going to learn what this means because yes, it can impact. But we can never be physically hurt by any space weather storm whatsoever as long as we reside on the surface of this planet. You can be right here like I am right now and all of you are. You can be on the top of Mount Everest. It don't matter. You can't be physically hurt by anything I'm talking about today. However, if you're an aircrew member or pilot, yeah, you can. If you're an astronaut, of course you can. That's where it can affect physical health. Otherwise, everything else is kind of a side effect from the things that are going on that impact the things that we're looking at. HF radio blackouts, the R scale. Geomagnetic storms, the G scale. The underlying thing that we're forecasting for from SWPC, when I say SWPC, by the way, it's SWPC, short for the Space Weather Prediction Center. Everybody just calls us SWPC. So if I say that, that's what I'm talking about. Solar proton events, that's what's driving the radiation storms. Solar flares, and these things called coronal holes. And the worst case type scenario, the big daddy of the storm world is the coronal mass ejection that we're really worried about, that's at such intensity that it could get us to the top end of that scale, the 5, the extreme end, and be lasting not just an hour, but some hours. That's our concern. All right, solar flares. What are these things? Well, they're giant blasts of energy that cover up much of the electromagnetic spectrum that we measure. We look at these and measure their intensity in X-rays. So who's all had an X-ray? Most of us, right? We go to the dentist, they give a lead vest they put on you just even for protection, even though the exposure is minimal. Always take these precautions. We measure these in X-rays. So how do we do that? Because our atmosphere protects us from harmful X-rays. We use satellites in space, like the imagery you're looking here off to the left. This particular flare happened back at the very end of the year, New Year's Eve day. How about that? The largest solar flare of the solar cycle up to that point in time happened just before the poor forecaster working that day had to get his forecast out. And it's like, you can see that's on the limb of the sun. Does anyone remember what side of the sun that is? East side. Thank you. Very good. On the limb of the sun. It does not matter where on the sun a flare happens. As long as the satellite we're using in space to look at it, which is, by the way, about 20,000 or so miles from Earth, the sunlit side of our atmosphere is experiencing the impact. That's why we can't warn on these. We have no way of knowing that they're imminent and about to happen. It's speed of light. The satellite sees it. We see it. The effect is already on the sunlit side of our planet, messing with the atmosphere that's going to prevent certain types of radio communication at 3 to 30 megahertz, high frequency, from bouncing off the atmosphere properly. So we measure these in X-rays. So if you've been to our web page, anybody explored our web page? Great. Some of you probably will from here on out, so now you'll know what to look for. If you start hearing about solar flares or they interest you and you want to see what's going on, we have an X-ray flux plot on our page. Most of what I show you is available on our page, by the way, straight up. Look at the scale on the right. That's an A, B, C, M, and X. The normal background of the sun during solar minimum in X-rays is at the A and B levels. And focus on the yellow-orange line, not the blue one. There's two types that we measure, but we're focused on the yellow one up above it. When we get to solar maximum, the background can be sitting all the way up in the C's like you see here right now. M, now we get into NOAA's space weather scale level. And M1, when we measure these in 10, so each of these letters has it can be a 1, a 2, so you can have an M1 through M5 up to M9, and then it becomes X1. That's where the letter designations come in. The reason I bring this up to you in detail is because this NOAA scale starts at M. That's where it's significant enough that we know that there can be impacts to HF radio communication. And there's a lot of entities that still rely upon that. And M5, the middle of the M, is a R2 event. And then it goes to every level above it. So X1 is an R3, and X10 is an R4, and X20, we can't really measure much well above that. That's the top end of the scale. So we can have estimated values above that. Back in February 21 and the 22nd, in less than 24 hours, there are 3 nice R3 level flares. So kind of in that middle, the strong part of our scale. 3 X-class flares, bing, bing, bing. The interesting thing about this is we at SWPC had to do something we haven't done before, because we live in social media world now. Everybody gets their news on Facebook or their favorite whatever it is that we all follow, right? A lot of us don't necessarily tune into the TV anymore. And what happened, if you can fling off the lights again really quick, maybe we can see it. On the bottom left over here, somewhere in the press world, somebody realized that flares were going on. Did any of you affected by the cell phone outage during that time? Yeah, maybe some of you were. There was a massive cellular phone outage. What's that?
This year?
Yeah.
I remember.
Yep. There was a massive cellular phone outage. And it happened to be around the same time these flares were going on. So people started messaging that in the broadcast world. The Pentagon is calling us up at SWPC saying, hey, what's going on here? These flares causing our cell phone outage that's being experienced. You know, it's national security is their interest here. People that are using that type of network on their phone. And we're like, no, we don't think so. No, but we had to message something we don't even alert for. There was nothing going on except these flares. We were already taking care of that. It should not have been affecting cell phones. But we had to message that out. We had to put out things to the press world and let them all know, no, space weather was not the cause of this cell phone outage. And what happened about a day later after we started doing this? AT&T or whoever it was came out and said, oh yeah, that was us. It was a software upgrade. You know, they were ready to blame it on us, space weather here. But yeah, you know, so what I guess I'm getting at is space weather doesn't affect everything. So if you start hearing something, don't freak out. You hear about the internet apocalypse or something, Don't worry about it. Just go to our webpage and find out what's really going on, because we're going to start doing that kind of thing as well. Being proactive about, now this is probably not space weather. I told you it affects things, even at the lower levels. This was just an R2, so an M5 to X1 flare. That yellow circle represents where the sun was overhead. You can see the sunlit side of Earth here. What happens? Well, aviation is impacted. They use HF radio in the airplanes flying across the Atlantic. They have to have it as a backup method. They use it as their primary method many times. They can't talk. If you can't make this out, it says ATC clearances and other message delivery times exceeded their time metrics. It was exceeding because they were trying to find a frequency that worked because they couldn't communicate with air traffic control. This is the kind of thing that we're doing all the time from SWPC, is issuing these things, and this is how users and the operators of the systems we use, they're taking actions based off those messages they get. Something I recently learned is that the State Department of our country plugs into all these same alerts. Why? And something I didn't even think about. We've got embassies around the world. Some of those are in third world countries. They don't have all the great luxuries we do with cell phones and everything. So HF radio, ham radio, is a big way they communicate. They need to know that they can't communicate during an emergency in the country that they're in, or if they need to get the word. It's really pretty fascinating. Back in 2017, the largest solar flare of the previous cycle, I think we're saying that that was an R4 now. At the time, it was just barely below an R4. Hurricanes were ravaging the Caribbean islands. People had no power, telephone lines were ripped apart, cell phones wouldn't work. They had to rely on HF radio to communicate with emergency officials, to talk to the United States, the mainland US here, to figure out what's going on and provide status. They couldn't do it because of the largest flare we had that cycle happened to be during all of that. So hours and hours went by where people couldn't communicate and get the message out and help themselves out to get the protection they needed, the help that they needed. So when you combine a regular catastrophic terrestrial weather event and a space weather event at the same time, that's what really becomes concerning. December 14th. Was anybody flying on December 14th? All right, December 14th, we had a flare take place. I told you location doesn't matter for a flare. This is all very true. So this one happened to be over on the west side of the sun. This was actually a pretty long-lasting flare, but it didn't get anything extraordinary. It was just an R3 level event. So it was just a strong one, not severe. But what happened? Flares don't impact other frequencies besides that 3 to 30 megahertz of HF. It's just the way the dynamics work. This one had an associated event that affected frequencies above that, and even up higher. Domestic airlines in this country, they communicate by line of sight with what's called VHF and UHF radio frequencies. For those that don't know, now we're going from like 30 megahertz to 300 megahertz and 300 up to like 3,000. This event had an unprecedented, what we call radio burst with it. It was so intense that what it did is it made aviation unable to communicate with air traffic control over our entire country. From coast to coast, for about 8 minutes, planes couldn't talk. It was so bad in Seattle that they were talking about ATC 0. Does anybody know what that is? 9/11, the terrorist attacks, that's the last time ATC 0 was declared in this country. That's how serious this was. They couldn't talk. Even their digital backup systems on those frequencies weren't working. Usually they're not so prone to this type of activity. Why did this happen? The sun does what it does. We can't predict a radio burst. There's no way we know about it unless we see the observations. Who gave us that observation? Yes, my old profession, the US Air Force. They report on radioactivity from the sun. The sun is a giant radio transmitter. It's sending out strength on all radio frequencies. In this case, think about it, December 14th, the sun is low in the sky. That map on the bottom there where it says highest impact, the sun shows that. That's kind of like directly overhead where it says highest impact. So it's kind of just on the horizon here in this country. And what happened is, anytime the sun was in the background with a plane, or air traffic control was in the background with a plane, they couldn't talk. They were being jammed by the sun. The background level of the sun on that frequency got to over 10,000 times its normal background level, almost 100,000 times. That's unprecedented. We have not seen that happen before. So now what happens? I told you we're always learning something new. Now the Federal Aviation Administration is really highly considering wanting to be alerted about when something like this happens again. And let me tell you the story of events this day, but it's really kind of interesting. The Air Force is extremely interested in radio bursts. I know why, because they support Department of Defense. So all the national security assets, and some of these things can be impacted by space weather. So they report on things that we don't necessarily do. But they're sending us reports about this radio information, and we're sitting in a meeting upstairs, some of us on the leadership staff, and I get a message in from one of the weather service units that supports air traffic control. And they're sending me an impact saying, hey, we had some frequencies impacted here. And I was like, okay, that's fine. I'm thinking it's HF. But then I look at the frequency and I see, no, this is line of sight VHF. That doesn't make sense. And then I got another one. So then I go look downstairs and I see this massive radio burst reported from the Air Force. It was so, I've never seen it in my life. And I worked at one of these observatories for 4 years. I didn't know they could measure that high. So I'm thinking it was a mistake. So I have Air Force is so important to us, by the way. We have an Air Force liaison officer that works there with us. I had him call up the observatory in Hawaii that reported it. They confirmed it and said, yes, it's valid. So then we're messaging that this is all going on, and they all got the word that it was space weather related. But this event lasted about 8 minutes. If it had lasted much longer, airspace was going to start shutting down. It was that bad. Solar radiation storms, the scary sounding one. What causes this? Well, now you have to think about energetic particles coming from the sun. We measure all sorts of them. Electrons and protons are the main ones. Protons are the ones that cause this right here. If you think about an electron and a proton, think about, all right, here's an elephant over here, and then you got an elephant over here, but they're 2,000 times more massive than the other elephant over there. That's kind of the difference between the mighty protons and the electrons. So you get these strong, massive, energetic protons coming in from the sun. They flood things, and they cause this thing we call a radiation storm. So now we're talking about the S1 through S5 on our scale. And I was never really going to talk about this as much anymore until I found out something that FEMA is going to do if we reach an S5. So I'm glad you're all here because you're going to learn some things you probably need to know if you ever hear this come through emergency channels and broadcasts. So what are these things? Well, these are the energetic particles. We measure them with that same satellite that we're looking for X-rays. We have our own scale here. But look here about what it affects. It can affect aviation. It can affect astronauts in space. Space launches, all the rockets that we're sending up. I mean, we're going to have space tourism pretty soon. Rockets are going up all over. A lot of them won't launch when we just get into the low levels, that 1 on our scale for these. Why? Because they can't risk these energetic particles penetrating into the electronics that have to be precise as they go up into space. And any deviation can make it go off course a little bit, can stress out the capsule, and it can explode. It can come apart. No, don't want to risk it. We're sending astronauts back to the moon. I can't wait for next year in the fall or so when we're going to have the 4 human beings in that Orion capsule going around the moon. It's been a long time. I'm really excited about it. But it's so important, this activity, that we're going to have a forecaster deployed to Houston Mission Control exactly for this kind of thing. Looking out for the astronauts' safety when it comes to radiation storms. Being the point-on-the-spot expert for this activity. By the way, these charts here in the middle, that's what we call a coronagraph in space. The nice eclipse that maybe some of you got to experience, all right, we make an artificial one. It's called the coronagraph. One of our satellites 1 million miles from Earth, always between the sun and the Earth as we revolve around the sun every 365 days, is looking at the outer corona of the sun for us. Look what happens here. This is a solar radiation storm running into the instrument. It turns into a blizzard. We rely on this to find things that you're going to hear about today. You can't see them anymore. Some satellites, they maintain their position by stars in space. Do you think they can find a star when that's going on? So they got to do other things to help maintain control of the satellite out there. This is some animations of imagery here. You might start to see that effect showing up here. Boom, something explodes from the sun. All of a sudden, we're seeing some fireflies dancing around on the sensor. That's a low-level radiation storm. We measure these at different energy levels. I won't get into all that, but just know that our warnings are based off this energy level right here, 10 MeV. A lot of other concerns that we're talking to people about are these other energy levels, and if you're wondering about what I mean by energy level, because I'm talking numbers and amounts, and I'm talking energy levels, well, think of somebody over here, and then like Wonder Woman or Superman over here. Who's got the more energy? the superhero, right? Same thing here. We have different energy levels of things that are roughly the same size. They're just how extraordinary they are. We get to 100, NASA is very concerned about it. When we get to 100 MeVs, getting to just 1. The amount of space that we measure, by the way, just to give you an idea, there's usually less than 1 of the particles we're looking for. When we get to just 10 of these protons, that's our first warning level. We're at S1. Now it's logarithmic, so that means every 10. So then you get 100, we're at S2, 1,000, we're at S3, and so on, all the way up to hundreds of thousands of these things at an extreme S5 event. That's going to harm things. Satellites in space are going to be impacted by that. And we really rely on satellites in space today. They keep going up. Small ones, big ones, low orbits, high orbits. It's going to be crazy if we have that kind of event happen out there. Coronal holes, if you can dim the lights again really quick, that's what these features are. So now we're looking deep into the corona of the sun with an instrument in space, and that's a massive thing, right? 109 Earths fit across the center of the sun. A coronal hole is an area where the magnetic field lines go further out into space before they come back and reconnect to the sun. That allows the natural solar wind speed to escape further into space. Who likes seeing the aurora or hopes to see the aurora someday? That's something you'll want to know about because that's the best way to predict further into the future about whether or not you want to plan your trip to Iceland or something like that to see the aurora. We'll talk about that at the end. Other things we're looking for, if you can dim them again, these things called prominences. Anybody who saw the total solar eclipse, maybe you saw some small one of these. Was the potential there to see something like that? Yeah, it could have been if it had been a week earlier. If it had been a week later, even more so, we had some strong prominences that were really sticking out far from the sun. These are billions of tons of solar material held in place by a magnetic field on the sun. Sometimes these things, oops, I don't know what I hit there. Sometimes these things will blow off the sun. You can even see the flare that happened here in conjunction with that. That is a filament eruption or prominence eruption. This is not only sending a whole bunch of material out into space, but it's carrying a strong localized magnetic field stretching out into space along with it. That's when we look for these things called coronal mass ejections, or CME for short. Could you have seen one of these during the eclipse as well? Actually, you could have, if one was going on. You wouldn't have seen it moving like you do here. That's a 4-hour window of each of these imagers you see here, of these CMEs. Just in 4 hours. Look how far it's gone from the sun. And these are massive. Could we have seen one during the 4-minute eclipse window? If one was going on, you might have seen a bulbous shape off the side of the sun. But it didn't happen that particular day and time. But this is what we're really keying on. This is the big one about the concern for our government in particular. Radiation storms because of satellites and effects that I didn't get into, and then these events. The fastest we think that a coronal mass ejection can get here to Earth, we think is 15 hours. That's fast, by the way. And you're going to find out on a timeline. I'm going to show you just how difficult it is going to be to message about that. The fastest historically has been 18 hours, but usually it's about 2 to 4 days. So that gives us time to do watches and then look for their arrival and put out warnings and then send out when its activity is actually picking up. December 14th, that super radio burst we were talking about. This is the coronal mass ejection that happened. I challenge you, you can barely make out the flare on the sun, but look at the size of the coronal mass ejection that took place in conjunction with that. That wasn't extremely fast moving. It was fairly slow. It clipped Earth. It provided some storming, but only in the lower levels. But yeah, it's not always clear if these are going to hit Earth or not. It may seem, well, you said the satellite was right between the sun and the Earth, so it kind of looks like it's going to hit Earth. No, it doesn't always work that way. The sun is weird. Space is weird. It's very difficult to measure these things and figure out how strong they're going to be when they get here and when that actually is going to be when they do arrive here. But this is what we don't like about them. Geomagnetic storms, that's what they cause. It's a fancy way of saying a magnetic storm. So as these CMEs transit space and they run into Earth, we have our 2-layer protection system, our atmospheric filter and our magnetic barrier, like a shield between us and the sun. And when these slam into that magnetic shield in the front, it spins up electric currents around our planet that can dump their energy onto the power grid. So now you start introducing a whole bunch of electric current that they don't like and don't want to see on their systems. Now this looks like a really complicated picture here. Can you dim those again really quick? The red lines, just focus on those. You can't make it out because it's not totally in focus here, but they come, the magnetic field of Earth comes out the bottom of our planet and goes into the top. So out the South Pole, into the North Pole. That means our magnetic field is pointed up, northward. You can turn them on again. So along comes a CME from space. I told you it's got a strong localized magnetic field carrying along with it. If it happens to be the same direction as Earth's when it arrives, it's like trying to put two negative magnets together, or positive magnets. They repel. You don't connect. Yeah, you'll get an initial pickup of activity just because of the strength of the arrival and the currents that generates, but then it might settle down, even though the potential's there for something much stronger. But if it turns south, or it arrives south, wham, you connect the magnets. Then things really spin up, and the activity can happen and escalate. The aurora can spin up and be seen in many parts of our own country, even at some of the non-G5 levels. They can be seen elsewhere. But the power grid is where it really gets in. I'm not going to worry about it on this picture. If you can dim them again. So if you go to our webpage and you're hearing about a coronal mass ejection coming towards Earth, and let's say we got a G3 watch out or something like that. Hey, I might see the aurora in Colorado with a G3. I'm interested in that. We've got a real-time solar wind plot from a spacecraft that's 1 million miles from Earth. And there's two things to look at here, two areas. That would be the one that says speed, which is the yellow line. You can see there's a sudden increase in speed. You can't make out the numbers, but that was like 400 kilometers per second. It jumped up to 700 kilometers per second. So almost double the speed. That's the CME arriving. The top one, the red and white lines, the white line is the magnetic field strength. In this case, that got to 6 times the normal background level strength. That's pretty intense. The red line, that's the thumb. What's the direction of the magnetic field? When it's above the dashed line, it's pointed north, the same as Earth. When it's the other way, it's south. So if you're looking for the aurora and you say, hey, and we hear something about it's arrived and you're waiting for night to show up, check that plot out, because that'll tell you if you're wasting your time driving out to the darker skies out by Greeley or something to look for the northern lights. Is look at that red line. Which direction is it going? That's a big clue to help you out. We've already had plenty of G1, G2, G3s, and even some G4s. The most recent G4 was just at the end of March. Very quick, very abrupt, and that's where this stuff I was just telling you becomes important, because I'll run through a whole scenario for you. But yeah, we've had plenty of these. This is what we put out on our webpage. We put it out on social media as these kind of graphics you see right here, trying to let the public be aware of what's coming. Not so much for them because they got to worry about it, but we know the aurora is of interest. And also, we get to that G5 level, they're going to be alerted about it through the emergency networks. A lot on this one. I'm not going to dig into details here. I just want to point out to you one thing. If you go to our webpage, you're looking for the KP index. The KP index tells you the level of geomagnetic activity going on. How strong is the storm? The 0 through 2 over here, that means it's quiet. A 3, it's unsettled. You're not going to see the aurora here. A KP of 4, we're putting our first warning out at a KP of 4, by the way. It's not even at NOAA Space Weather Scale levels yet. KP of 5, that's a G1. Now we're at NOAA Space Weather Scale levels. When we get to a KP of 5, a G1, we're picking up the phone and calling 2 power companies in the north part of our country, one in Wisconsin, one up near New York. Why? They want to know about it already. Not that they're going to have any impacts, but they got to spin up some procedures, have something ready to go, just kind of be ready. That's our job, is inform things like this so they can take mitigation measures to make sure everything still works. KP of 6, that's a G2. Now we're talking to air traffic control out in Oakland. We're talking to a few more power companies, and we're calling up NASA. That's what we're all doing from the forecast office. A G3, KP of 7. You're all, hey, maybe I'll see the aurora now. Now we're on the NERC hotline call. I'll explain that on the next slide. KP of 8, G4, we're talking to FEMA over in Washington, D.C. and down at Denver because they're the alternate center for FEMA. Now they want to know. And even the White House is starting to get word about it now at a KP of 4. A KP of 9, the G5, the top end of that scale, we're talking to the White House Situation Room. Why? Because now we're at levels that we think the power grid is at risk. And when I say the power grid is at risk, this is what I'm talking about. On that NERC call that I talked about, the hotline call, this is everybody that gets on that call. All 18 or 19 reliability coordinators throughout the country are on that phone call through our interconnected power grid system because of the threat of currents building up on the high voltage transmission lines that can knock down the power grid. It's happened in the past. and they don't want to see it happen again. And then we alert on them at every single level we get from there. Whoops, did it again. So this map here is something new we have. It's called a geoelectric field model. Don't worry about that, what it means, but I'm showing this to tell you kind of what's going on behind the scenes. So we make these phone calls. This is what they want to know about, is how much voltage is showing up on their systems that shouldn't be there. Normally we're measuring this in millivolts. That's thousandths of a volt. When we get to just 1 volt per kilometer, they're noticing it. We get to 10 volts per kilometer, it's causing actions. It's making things, they're doing mitigation measures. Things that are in place that are supposed to help mitigate the problem start working and doing their job. You get to higher than that, now you're talking about problems, potentially. And just like any weather thing or radar, you kind of know where the concern is. Just look for the dark blues and purples and white colors. In this particular map here, it's somewhere around 12 kilometers. And this is from a 1989 storm. This took down the power in 2/3 of Quebec, Canada, this exact storm right here. The northeast part of our country, the entire northeast, came this close to losing power as well and collapsing. So people would have been out with power in March of 1989, freezing temperatures for hours and hours, days, even weeks in some cases. We all want to know about the aurora, right? Well, G3, that's what you want to look for here in Colorado. Yes, you can see it. G2 or even maybe a G1, because for reasons I won't get into, there's all sorts of deviation and changes that happen. But G3, that's when you might want to start paying attention to see if you have a chance to see them here in Colorado by visiting some of the things I was talking about. A KP of 9 event, a G5, that's not even close to what the biggest event we know of. This, by the way, kind of tells you where the aurora may be visible. The red's kind of like, it's very high in the sky. The green is maybe a little lower. One of the events we're going to talk about, that oval would have gone all the way down to here. That's catastrophic today. What are we doing? I talked about some of this already, but this is who we're communicating with when we started getting to the 3, that NERC call, the 4 levels and the 5 levels. Now we're talking to all these entities, or they're talking to each other amongst themselves. This is the thing I want to point out. When we get to an S4, the radiation storm of a 5, or a G5, FEMA's going to fire up their warning system that's going to go down to all the local government levels. That's when you're going to hear about it. People are going to hear about a radiation storm, an S5. I don't know what message they're going to get. I don't know what the message they're going to get for a geomagnetic storm, but it's going to go out to the general public. The broadcasters are going to pick up on it. I can't wait to see that happen because I don't know what they're going to say. Most people don't know about any of this stuff, right? You're all smarter than 99% of the world on this now. So you know what this means now. You know what to expect and be ready for. But yeah, I wasn't aware of this until recently, that they actually messaged down through their system like a national emergency, this information. We're in prime time. I told you this year, next year, even to 2026. For reasons I won't get into, the astronauts that are going to go back to the moon, even though it's very unlikely, they're at their highest risk in 2025 and 2026 for a radiation storm. So it's going to be fascinating. Hopefully nothing happens. Have we had it happen before? We came really close. In 1972, right in between the last 2 Apollo missions where we landed, at the time, just men on the moon. 3 months earlier, they were up there. Apollo 17 was 6 months later. Right in between, we had an S4, potentially an S5 level storm going on, came close to that. It's thought that that storm was so intense it would have caused extreme radiation sickness to the astronauts, and there's still speculation about whether it would have been deadly or not. That's the risk we're talking about. Here's that Carrington event. This is the 1859 event. This is what we're worried about today. So in 1859, there was an astronomer named Richard Carrington, and he was drawing a sunspot group from his observatory you see over there on the left. Geez, I'd love to have a home observatory like that. But anyway, he's drawing the sunspot group here, and you can't, maybe you can make it out. The letter A is pointing to a little bright orb there. He didn't know it at the time, but what he was drawing on his sunspot drawing was something that's very rare. It's called a white light flare. That means the flare was so intense it went into the visible spectrum and it outbrighted the brightness of the sun. And he saw it in that sunspot group. And he put it on his drawing. 18 hours later, the sky lit up. I mean, the aurora was seen down in Cuba. Hawaii saw the aurora. This thing was unbelievable. People thought there were fires in the distance here in Colorado. There was panic going on. People in Europe thought the world was going to end because they'd never seen this before. They didn't know what to make of it. That's the power of an extreme. G5 is the top of our scale. You can have a G5 that's here, or you can have a G5 that's through the roof and another 3 stories up. We think this was in the one that was almost the 3 stories up. We know it's happened. Telegraph operators, that was our technology. Slapping metal plates together, hooked up to a battery, and sending a signal across a copper wire to one territory to another in this country. Batteries were sparking. Stations started on fire. There's a documented conversation with, I call them ditty boppers, between 2 of them that were talking. They decided to disconnect their battery. They did. There was still a signal. They could still carry on a conversation with no electricity hooked up, no battery. That's the power of this storm. That's what we're concerned about today. Some notable, I guess you'll have to dim the lights. I got some red here. The Carrington event of 1859. That's our benchmark when we're talking about a catastrophic space weather event. The Quebec storm of 1989, I already told you about that one. The Halloween storms of 2003 didn't take down our power, but it took down power in Sweden and South Africa. Afghanistan, 3 soldiers were killed because of communication issues. They needed information, they didn't get it, they were killed due to space weather storms that were going on. 2012, we had a Carrington level event, we think it was, but it went sideways from the sun, not towards Earth. Just 2 years ago, 49 satellites went up thanks to SpaceX. A day later, 38 of them burned up in the atmosphere and came back down to Earth. They should still be up there. That was from just a low-level geomagnetic storm. The industry needs to get smarter about space weather. Even more recently, in March of 2023, I hope that, let me go back a little further. Get that, there you go. This CME happened on the sun. This was on the far side of the sun. This was at Carrington level speeds. We don't know if it would have been a Carrington level event, but it was at that speed. What I did not tell you about radiation storms, and this is where this becomes very interesting and concerning, is those energetic particles, they're locked to magnetic field lines. So the magnetic field lines come out from the sun and then they kind of curve because the sun's rotating. They're locked to them. They don't cross them. It takes a lot of force to cross them. So that's where location does become important on the sun. If they're on that left side of the sun, that east side, or even in the middle, they're going to come out and curve away from Earth. If they're on the right side, that west side, if it does one of these events, they're going to come out and curve right towards Earth. That's when they can get here in as fast as 15 minutes. Otherwise, it may take 24 hours. This event, on the far side, almost exactly 180 degrees opposite Earth, gave us one of these radiation storms at the one level for 2 days. It was that strong, it crossed that many field lines all the way around until it got to ones coming towards Earth. That's force. That's potential. That's near the levels we're talking about for catastrophic storms. So one of the things I'll be finishing up with here is just back at the end of March. We had a G4 storm, but we had everything happening. We had sunspots on the sun. I was working the evening shift when these flares kicked in that you're seeing here in the office. And you might look at the one up at the top there and you might think, well, that's only one big sunspot, but the one down south looks a little more impressive. And yeah, our forecast was built for flare expectations, was based off all that analysis. Well, we had these 2 giant flares kick in on the sun. Well, I also saw signatures that told me there was probably a coronal mass ejection with this. And we're running a radiation storm prediction model, and that's telling us there's a 50% chance that that flare in the middle of the sun had enough force to cross field lines to get to Earth. Well, I left work, the night shift came in, up started going the particles, the energetic protons started showing up, sure as heck. So we had to issue out an S1 warning. It became an S2 later, and we almost got to S3. That means thousands of them. This is what the coronal mass ejection looked like, and you can see the radiation storm kicking in at the low levels with the flashes of light going on. So he starts analyzing the CME as well and ends up putting out a G3 watch for about 2 days out. Then the CME arrives a little earlier than expected, almost 12 hours earlier. It was that quick. And you can't make it out very well, but you can clearly see how the yellow lines jumped up here. We got to 800 kilometers per second. The field strength went up to almost 7 times normal background level. But if you can dim the lights again. Oh, yeah. Sorry, thank you. It's just not coming out very well, is it? But you can't make out the red line so well. But initially it arrived, maybe you can see it, it was south. So the CME slammed into Earth's protective barrier. It turned south, it arrived south. Everything connected. We went G1, G2, G3, G4, just like that in a matter of like 3 to 6 hours. We were all the way up to G4 levels. The geoelectric field model was showing a couple of volts per kilometer in Canada. So we're making our phone calls to the power grid of North America, and we hear them talking as we're giving our information. We hear, yeah, we're noticing we've got amps. I've never seen them this high on our grid, but they're taking their mitigation. We even hear that one of the inhibitors that helps prevent some of these from building up tripped. It means it did its job. It's deflecting current. That was just at a low end G4, and it was just a quick G4. But then the red line went north. So that you can't make it out, but that white line stayed at 6, 7 times strong background for almost 24 hours, but the red line, it pointed north the rest of the time. This CME arrived right about near noon, so daylight side of our planet, and then it turned north. So if that had been staying south, we would have had G4s running through the night. It really been quite a marvel for an auroral show around here. What would a Carrington level event mean today? Well, this is kind of an idea of what that might be like. It would take some time to see the CME because it takes a while for the imagery to catch up, and we can look for the chronograph imagery. So we'll see a flare, we'll see something going on, we'll know there's probably a CME, but now we got to wait, unfortunately. It's not real time. So maybe by 4 hours, in the best case scenario, we probably have enough imagery that we can start doing an initial analysis of a coronal mass ejection. About 8 hours later, we'll have our analysis and our model runs complete. About 10 hours from first CME first happening, now we're talking to other countries, including the United Kingdom and Australia, because we all have to have a common message here. So we collaborate with international partners from SWPC. It's pretty cool. Now we may finally get a watch out in 10 hours in the best case scenario. G3 or G4 watch will be issued. We don't do a G5 watch. We stop at G4. 10 to 12 hours, at that point in time, plus 10, 12, we're going to be messaging. We're talking to FEMA, we're talking to headquarters, we're talking to the White House, whatever, because of the expected event coming in. Doing briefings, interviews with the press. About 15 to 24 hours. We're talking Carrington level event here, so it could be that quick. CME arrives 1 million miles from Earth, the satellite picks up on it. We start issuing warnings from the office. The power grid. This is the United States Geologic Survey prediction of what that Carrington level event would look like today. I told you 10 to 12 volts per kilometer is a problem. 100 volts up to 900 volts per kilometer. This is the catastrophic thing we're concerned about. I hope we don't see this in our lifetimes, but this is the concern of why this is being funded, why we're doing this work, is for that kind of thing. So in it would arrive, we'd be putting out all the alerts all the way up through G5. We'd be continuing to keep these up. The broadcast systems I talk about would be initiating their alert system, and I don't know what that's going to sound like or mean. And the public's going to freak out, right? They're going to hear about an S5 radiation storm or a G5 geomagnetic storm. So I'm trying to be proactive about educating as many as I can about what this all actually means. There's going to be power problems, guaranteed, this kind of event. So we're going to have to do like an all clear and let them know the things so they can start doing recovery. What does recovery mean? I don't know. It means how devastating this would be to our grid. But that's what we're expecting for a Carrington level event based off known science and data. And just to scare you a little more, we're overdue. We're overdue for this. We've seen them. They've just been going the other directions. But eventually one of these is going to come towards us here. How do you stay informed? You visit our webpage. Just about everything I've talked about you can find for yourself on there and kind of follow along just for general interest. Or if you want to think about the aurora, you can subscribe through our product subscription services here, and you can actually get things to your email that tell you about things you're interested in. Warnings, watches, forecasts, whatever. Plenty's out there for you. This is the strongest flare we've had this cycle so far. It was very impulsive. Most of these flares means they're just lasting a few minutes. Then they come right back down. That's the Associated Sunspot Group. Remember the coronal hole? We got a coronal hole down here as well. So a lot going on here. But that's the largest one so far, and it was just a X6, not an X10, not an R4, so just an R3. All right, so I'm just going to wrap up, talk eclipse pictures, because I know some of you are going to be talking about that, right? So if you can shut them off again real quick. Yeah, that's me standing in the forecast office. But yeah, this is I didn't go to this last eclipse. We had to cancel our plans for a wide variety of reasons. But back in the annular eclipse, I was taking pictures from my backyard of that. You can see the sunspot groups there. I was kind of watching it cover up the sunspot group from the moon there. This is my second eclipse. I was lucky enough as a kid to be in middle school, and a total solar eclipse went right over Williston, North Dakota, where I'm from. Loved it. Didn't know anything about photography then, but poor Cindy here, I had to drag her along a year after us getting married. Say, hey, you want to go to El Capoco? Yeah. Okay, we're going to see the eclipse in Mexico City. So this is my photograph with an old film camera, Pentax camera, from that eclipse down there in Mexico. This was about, remember that 1989 storm? Just 2 years after that. You can see a nice prominence down there in the bottom. This is the eclipse back in 2017, kind of watching things get covered up. I took these up in Torrington, Wyoming. Then the total eclipse itself, covering it up. You're all familiar with that. But here's what I wanted to kind of show you that's kind of cool. You can take science and use it to this. So here I took my picture. I was doing this because a lot of people wanted to know what they might see during the eclipse. So I was teaching science. So what I did is I took this picture right here, and I said, okay, let's take a coronagraph image from that same time and overlay it with my picture and see what we can find. So you see these coronal streamers, the one going up to the top right, the one to the top left, another weaker one down to the bottom right. So let's take my eclipse picture and put it in there, and look at that. You can see the streamers. Of course, I had to reorientate it, right? But there they are. You guys should do the same thing, whoever took these pictures, see if you can find anything like that. But yeah, pretty cool that you can bring science, right in your backyard and look at things that we're looking at. And there's my big diamond ring picture from the 2017 eclipse there. Anyway, so that's it. Been my pleasure to talk to you. I'm happy to answer some questions before you continue on. And I gave you a lot of info.